Well, now that we have three-dimensional space, we could imagine that the component form of a vector in R cubed is just what you would guess the vector. I guess I could make that boldface there. Vector V would be in component form ABC. And the standard form for a vector would be also what you would guess. Vector V is AI plus BJ plus CK, where K is a unit vector along the z-axis. K, in fact, in component form would be the vector 0, 0, 1. So we could look at some properties and formulas concerning these vectors, and it's pretty, and also with scalar C, and it pretty much mirrors everything that you've learned about vectors in two-dimensional space. So, as a for instance, vectors u and v are equal if and only if u1 equals v1 and u2 equals v2 and u3 equals v3. See, only adds one extra dimension, but this concept is still the same. The component form of w can be represented by the directed line segment from the point P to the point Q. Then W is Q1 minus P1, Q2 minus P2, Q3 minus P3, which is exactly what you would have figured it would be, because it just has this little additional third component. And the magnitude of a vector, of course the length of the vector V, is found the same way. It's really just the distance formula applied in three dimensions. So the length of vector V is v1 squared plus v2 squared plus v3 squared. That's this v1, v2, and v3 from this up here. And a unit vector in that direction is 1 over the length of v times the vector v. Okay, this is the scalar times that vector v, and of course that result is a vector. The sum of the vectors, you guess, add the components. You mean add the third component also? Of course. Scalar multiple, you mean you multiply the first, second, and third component by the scalar c, of course. So, and vectors in 3 space are added and subtracted just as in R squared using parallelograms. So if you think about it, a vector in 3-dimensional space and another vector that you're adding to it also form a parallelogram in a particular plane that both vectors together would be what's called spanning. So, we got time for one example here. Give a unit vector in the direction of I minus j minus 2k. Okay. So first of all, we need to know the length of this vector. That would be the square root of 1 squared plus negative 1 squared plus negative 2 squared. So in other words, the square root of 1 plus 1 plus 4. That's the square root of 6. So 1 divided by the square root of 6 times the vector v I minus j minus 2k. If you wanted to write that 1 over the square root of 6i minus 1 over the square root of 6j minus 2 over the square root of 6k, more power to you.